So now let's look at this couple of different lab models that we will consider in the labs that we run. And what we want to do in the lab is set up a mass spring damper system that's gives consistent results. Sometimes we've tried just hanging a spring from a mass, but that's you want to constrain it because you want it to follow the model that you are defining. So using sort of beam type springs with masses are nice because they don't oscillate in multiple directions. A little bit easier to control. So we've actually used the beam before that you have used for, say, the strain gauge by just putting a mass, and actually sometimes the mass here that we attach is an accelerometer. So we have a mass spring system. And then the stiffness is relatively easy to calculate, right, for that beam. And we've done that for that experiment. But we're actually introducing another one here is using this flex guide design that we've talked about. So here's just one story of that, and this is again also nice because it's constrained to move in one direction, and also you can show that the stiffness of these flexes can be calculated similar to a cantilever beam, but you have to take into account the number of these you have. So that's n there. So for the system we have, actually each story has 4, so you'd put a 4 in here, and then you could estimate the stiffness if you knew your Young's modulus, the length, and your area moment of inertia, right? And this is again a nice system because it's relatively easy to build. As you'll see in the lab, you can put multiple stories, and that's kind of what we'll do in the second week, is to look at, we'll go from a single story to a 2-story system, having multiple degrees of freedom. So what are some things that we try to do in this lab? Well, again, we're trying to illustrate measurement. So we're going to be using an accelerometer, but also take an opportunity to say, oh, look, we have that model. Let's try to see how well we can estimate the parameters that we need for that model, mass and stiffness for the components, given geometry, given material parameters. Usually that's pretty straightforward process. There's usually some uncertainty, but you can then verify or improve those once you get into the lab. And you can try to understand, where might my equations say for stiffness or my estimates of mass, where are those off? And that's something that we're trying to do with this lab, is to show you. And remember, the value of that might be is if you're ever designing, some kind of system where you're having to take into account its resonance and you're trying to make decisions on mass and structural design. You can see here how well some of these basic equations might work for predicting what those resonances might be. Damping is something that's very hard to estimate theoretically. A lot of times you're going to have to go into the lab, and that's what we're going to do. We're going to have to measure the system motion to basically extract damping ratio, and then from that we can estimate the B value, and I'm going to talk about that shortly. So that's one of the other things that you're going to be doing in the lab. And then also, even though we can theoretically estimate undamped natural frequency, damped natural frequency we can't. So these kind of go hand in hand, but we're going to look at what it takes to estimate those values. And once you get into the lab, of course, we want to see how well those system parameters can be estimated, and also once you have them, how good is that model in predicting the actual measured response? So we can compare the theoretical predictions to the measured response. And keep in mind, since we're measuring acceleration, you're going to be comparing acceleration. So remember, the solution for this mass spring damper system was for the displacement. So for the damped case, you're going to have to differentiate that solution twice to get acceleration, so you can compare those acceleration to the measured acceleration, right? Or you might think that you can take your accelerometer measurement and try to estimate displacement from that, since that's the solution you have. That's another little challenge for you that we're going to introduce in the lab. Can you integrate the acceleration to get displacement? How well does that work? and so we'll give you an opportunity to do that as well. Okay, so let's take a look at the first few steps before we before I show you how to estimate some of the other parameters, the system parameters, natural frequency and damping. And I'm just trying to show you, when designing this experiment, just kind of sketched out the concept of this flex guide using these U channels. And what I have done is on the course log posted the actual materials, raw materials that we bought off the MasterCar website, so you can look at the actual design and note the actual size that this came out to be is 5 by 5 here, right? And these beams are 7 inches, okay? And also there's some screws here. I mentioned that in the pre-lab. So in the pre-lab, what I want you to do on the first one is actually just estimate the mass. There's the U-channel piece here, and then there's a clamp piece on both sides that clamp this tempered steel part. The tempered steel is what's making these flex guides, and that's what you're going to need to take into consideration in estimating the stiffness using the relation I just showed on the previous slide. So I've shown you some of the parameters here, and also there's some screws here. By the way, the screw set here I gave you, it's about 5 grams each. This is aluminum for all those the mass pieces here, tempered steel for these flex elements. Okay, and I found that you might use a nominal value for aluminum, and it's going to be a little off. So once you get to the lab, you're going to have to probably update your values, but you'll come relatively close on the mass, and possibly on the stiffness too. But there can be some uncertainties, and that's kind of what I want you to explore a little bit and see where you think you might be off.